so we want to take advantage of the technology, what our GPS, our Earth survey satellites, our smart city gadgets, our smartphone, all these Internet of Things feeding us, right? There's a whole lot of data being generated every second, everywhere on Earth now. And then making it useful to solve the problems we identified earlier. So we all know that data can only be useful if you can process it and make it as informative information and become knowledge and become decision. And in that, knowing where is the foundation. But not only knowing where, but also knowing whether they are connected in certain ways, what is the distribution pattern on location, what is the relevance, what is the causal relationship, what is their connectivity. So all these are what we call geospatial analytics. And you could also call it spatial data science. It's pretty much in the old name was geographic information science. Doesn't matter what you call it, you need to process data, gather it, process it, understand it, explore it, model it, visualize it, and then re-understand your problem, and then we go on to the cycle. So that means you want to have access to data, integrate them, visualize them, perform high-speed computing to analyze them, and then make that process replicable so that you save time next round when you have to tweak something and rerun the process. And then you need to collaborate with people as well. So all those challenging problems doesn't take only one specialty domain to solve. So collaboration. And then when you collaborate, people come in with different backgrounds. You can't expect everyone to write code. What do you do when you share data and share your simulation? So people try to solve that problem, and the government develop platforms like geodata.gov. That actually website no longer exists. It was the one-stop shop for geospatial data in the U.S. federal government. Now NOAA still has its one-stop shop for NOAA data. Much of it was geospatial as well. Esri, the leading GI science company, has its ArcGIS Online platform. Google has Google Earth Engine. And DataVerse is our own product, Harvard University's Institute for Quantitative Social Science, where our Center for Geographic Analysis is part of. That's our own system. All these systems provide data metadata download. Some of it provide query and preview of the data. Some of it allow you to share, edit, online analysis, publishing, preservation. So partly solving the problem we identified earlier, but all of them are facing challenges because these systems are costly to develop, costly to maintain, take specialty skills, not so flexible when it comes to accommodating all kinds of analytical needs from all sorts of domains. So researchers with different backgrounds come in often at a loss and very hard to talk to each other. So that's the problem we identified, and that's why we started a project called Spatial Data Lab Virtual, trying to tackle this problem. And that is to build workflow-based modules, case studies, and push it to a web portal so that people don't have to deal with installation, don't have to deal with software licensing, and they can browse through the cases built by someone else, identify what's useful, expand that, test it out, use it for teaching, use it for decision-making, use it for research, and it streamlined the life cycle of spatial data science. So this project is sponsored by the National Science Foundation in the U.S., It's part of a innovation center called Spatial Temporal Innovation. And it's a research conducted here at the Harvard Center for Geographic Analysis, and our partners at George Mason University hosts the web portal for this project. And most importantly, we have KNIME, the company who provide us the technology for workflow building. And then our Future Data Lab is a nonprofit organization sponsoring the education arm of our project. And we all work together to achieve this objective of making data integrated, spatial data integrated and available through the cloud, and having executable analytical tools with case studies packaged from data, tools, visualization, report, and education module streamlined together. So we choose KNIME because first, KNIME has an open source foundation of the desktop analytical platform, and we can build workflows from there. And then KNIME also has that web portal allowing us to publish and directly interact with end user without asking them to install anything. And in between, I think the KNIME's flexibility of allowing snippets of code to be wrapped into the nodes, allowing for community extensions so that we don't have to wait for KNIME to give us all the tools. We can build our own and be part of KNIME and work into our case studies. And then eventually the good ones and most useful ones, KNIME accept us and work with us to make them native nodes and package them into a KNIME extension, which is the Geospatial Analytics Extension that we're going to show you here. So we have almost a track to develop tools gradually integrated at different level with the KNIME platform and making it available for everyone. So the idea is that our professionals and researchers and students all can install the platform, that desktop platform, which is open source. Anyone can download and install. And we'll teach them how to build their tools, jumpstart from our repository of already built tools. And if they like it, they can run it. If they don't, they can change it, push it up to the KNIME server, integrate with data coming from the cloud. They don't have to have all the data locally, and then push it to the web portal. Now end users can use any gadgets with a browser to adjust parameters, change data, and update the visualization, the report, and the charts and tables based on the rerun of these tools. So that achieves our objective of supporting data, research, learning, teaching, and application for decision making. From here, I hope I didn't run over the 10 minutes timeline. I will then pass it on to Dr. Liu, who will give you a menu for you to choose which one to look at, what we could do.
Okay, thanks, Wendy. Okay, and because I do take a lot of time to building workflow and building the KNIME Geospatial extension, so I may be too excited, so please stop me when I get too high, okay? So I have 6 case studies here. So the first 3 case studies come from, is developed maybe several months ago, and which has been presented during the KNIME Summit at Austin. And another 3 case studies is built recently. And so I would like to you or the users online to choose. Maybe you can choose 3 of them. I can play 3 of them for you. And another thing I would like to mention that the first 3 is the voice used by my own voice, and the last 3 is using the AI technology. So it's use Microsoft Azure fake voice. So, okay, is there any user choose on any of the cases? If not, I will choose randomly. Oh.
What about the online?
Okay, 2. Okay, like 2. Okay. Any other choice? We can play 3, I think. 6. 6. Okay, 2 and 6. Addition. Another one.
Why don't we can start there, then I'll grab another one from the online community.
Okay, and all the 3 cases can be accessed on my YouTube video. If you search Geospatial, KNIME Geospatial Analytics, so you'll get all the videos. So I played the 2nd and the 6th, and the 6th is our new geospatial nodes. You will find what the new features are on our next version. So okay, I'll go to the
number 3 has been chosen as well by our online community. So 2,
Okay.
3, and 6.
Okay, 2, 3, and okay.
So you might want to exit and then go back in. So what you want to do is do this. So you can
jump to
jump down to case
2 and 3. Okay, thanks. Thanks. So for this case studies, we use the case studies to know how to solve a question. If we want to choose 5 hospitals to vaccine citizens in Austin to minimize the total travel cost. So here we will use 3 kinds of data. The first one is the where the residents are located. So we'll use the U.S. Census data and the U.S. Tiger map is a built-in node in our geospatial extensions. And they will use the geocoding to get a hospital location. So this is the second data source. They will use some very popular tools such as spatial drawing, and they use Euclidean distance, and they use P-median nodes to solve this program. So then I will play the video for you. Okay. Why there's no voice here?
sound is not connected. Try.
Okay, I just stop. Okay.
Yeah, I just hear because of the echo.
Yeah.
No, you can try it. Let's try it. If it works.
The second case study is about site selection. Public facilities. Companies can profit from a good location. For instance, in Austin, there are many hospitals. If we want to choose 5 hospitals to vaccine citizens in Austin to minimize the total travel cost, how can we answer this question? First of all, we need a population of every census block groups. Then a base map with geometry information will be utilized to combine the population information, taking the centroid of the census block groups as the representative spatial point. Then, with the geocoding of hospital locations, a Euclidean distance tool will be applied to calculate the travel cost. The final step is using corresponding site selection tools to solve this question with the arrival of distance and the population. Based on these new nodes in mind, we can build a workflow for this question easily. In this workflow, we use the US Tiger Map node to get the latest space map at the block group level for 2020, and the US Census data node to get a population. To use this node, users need to request a free US Census API key, which can also be used in another node, the American Community Survey 5-year estimate node. Then, we can combine them and convert the polygon feature to centroids. After the transformation of hospital coordinates, we can get a distance between census block group units and hospitals by using the Euclidean distance tool. Then, the P-median tool can be utilized to assign the optimal hospitals to each census block group using the 2 key variables. We can compare the result to a random selection based on the partitioning node and the nearest join node. The result showed that the average distance was reduced by 26% compared to random selection, equivalent to a reduction of 484 tons of carbon dioxide emissions for all citizens of Austin drove to the hospitals, which could probably take more than 24,000 trees to absorb it in a full year. If we have a limited budget, we have to select only 3 hospitals. In this scenario, we can change the percentage to 13% in the partitioning node and also set a parameter in the p-median node to 3 and rerun the model. At this time, the results show that the p-median average distance get a reduction of 27%, equivalent to a reduction of 565 tons of carbon dioxide. So site selection algorithms do help us to save the money and contribute to global sustainability. Okay, so this is the second case study, and then we'll go to the third case study. So which is okay, I'll go to this one. So this one is so okay. So for this one, we also use 3 kinds of data. First one is the census data. We need to know where the population and where no spatial distribution of the populations. Second one, we use the twist data, which is harvested by our colleague at the Harvard CGA. And also we use the data of the Florida, the Hurricane Ian's trajectory, maybe several months ago. So use this data and our new geospatial nodes, we can we explore the impact of the Hurricane Ian, which mainly on the sedimental changes. In terms of impact analysis, often we want to use multiple data sources to understand spatial events and their impacts. As we all know, just a month ago, Hurricane Ian struck Florida. To understand the impact, we need information on Hurricane Ian's trajectory, population, and the geotechnical trees in Florida. Likewise, the nodes for the U.S. Census data and the U.S. Tiger map are for the base maps and population. Multiple rain buffer nodes get buffers at a different distance from the Hurricane Ian track. Overlay is used to assess the population of different buffers. Through twist data collected by Harvard CGA and the spatial join node, we can understand how people feel about Hurricane Ian. Here is a workflow. In the first part of the workflow, the geofile reader is used to read the hurricane route. The multiple rain buffer is used to get the buffer zones affected by Hurricane Ian. And by dissolving the nodes, we can calculate the total population of the different areas. The result shows that the buffer zone from Tampa to Jacksonville was the most populous place and endured the greatest challenges. The second part of the workflow contains a dataset of over 100,000 geographic trace records with the keyword Hurricane Ian, pre-processed in Harvard FASRC, and assigned a sentimental scores. Here we use the Kepler GeoView nodes to help us to visualize it easily. In wraps, the Kepler GL function, we can change the color settings by sentimental score as needed. We can also use filtering to examine time series changes in sentimental scores. We apply spatial joins and divide the trees into 2 phases, before landing and after landing.
with the key date of September 28th. Before the hurricane made landfall, the 50-kilometer buffer zone at the center of Hurricane Ian's predicted path had the lowest sentimental scores, which is understandable, where those in the nearby 100 to 150-kilometer buffer zones were very optimistic. But after the hurricane made landfall, the situation was just the opposite. The sentiment of people in the 100 to 115-kilometer buffer zones became relatively negative. The possible reason is that the residents of those buffer zones did not prepare enough for the extra large impact area of Hurricane Ian. These sentimental scores changes in the two stages could further highlight the difference. People who were in the center of Hurricane Ian's path were obviously relieved and showed more positive changes like those on north and south side of Florida.
Okay, so many users have told us they like the GeoView nodes, Kepler GeoView, and this node is developed by my colleague Xiaokang Fu here. And we would like to present more visualization and geospatial analysis functions. And we'll also welcome your feedback, and we will keep working on that. So then I will play the 6 case studies. I think you are get the right choice because the last case study is developed just yesterday. So it's just wrapped 3 the new nodes will be released next month. So this can, and it will also meet the needs of our previous users because after our the first release of our geospatial extension, many users told us, why don't you provide nodes to calculate the distance based on the street network, call them to do some routing, finding, or to do some OD matrix calculation. Also, someone told that we need some geocoding. Yes. So here is what we have provided for you, and we want to grow with you, the users and the communities. So I go to the last case study, and okay. So for this one, I will use. I'll introduce 3 new nodes. The first one is. Okay, first one is a street network matrix. It accepts 3 input data. One is where's the origin point, where's the destination point, what's your street network feature. So these 3 nodes you will provide us. Then you will specify the speed column. So this will be 4 parameters. Then we have another one is a Google distance matrix. So for this one, you might provide your own Google API key. And the last node is isoprom map. So if I stand here, in 5 minutes, how far can I reach? Or in 15 minutes, how far can I reach by bike or by walk? So this is the general idea of this case study. And this case study also answer a question. So help us to find the accessibility to hospitals in Baton Rouge. So here's the case study.
This case study will show how to use the new spatial network nodes to estimate the accessibility to hospitals in Baton Rouge. First, create a new workflow and drag a CSV reader node to read the prepared hospital address data. Then we use Latmon to geometry node to transform it into geospatial data with geometry information. For residents, we use census block group data in Baton Rouge and use local file browser configuration to get the shapefile path as a flow variable which is fed into a subsequent geofile reader node. Repeat the previous step to read the road network data. Then we can use street network matrix node to calculate the travel time and distance matrix between residents and hospitals based on the origin, destination point, road network, and speed information. Before using it, we need to transform the speed in the unit of meters per minute. Here the original unit is miles per hour. The result contains the origin ID, destination ID, duration, distance, and snap distance, which are the distances between the OD points and the road network. We can also use another node, Google Distance Matrix, to calculate the OD matrix, which only needs the origin and destination point information. But the user might provide their own Google Distance Matrix API key. We might notice that if the data is not a point feature, it will be transformed as its centroid while calculating. Further comparison shows a persuasive correlation, 0.93 and 0.97, between the results. Scatterplot can also help us understand the difference between the two ways of OD matrix calculation. Then we can use group by to get the minimum travel time to hospitals and map it with geospatial view nodes. Obviously, the residents in urban areas have better accessibility than those in suburban areas. We can easily change the accessibility standard as the mean travel time. If we want to know what is the service area of one hospital in terms of travel time, we can use another node isochrone map. Before using that, we need to calculate the travel time for each road segment. Then use row filter to get one hospital and link the two data to the isochrone map node. In the dialog, set time as travel cost and input as interval values. Their units are consistent with the column time, which is minute. Users can explore the result by geospatial view node. Please notice that all the input data can be acquired by the OSM POI and OSM boundary map OSM road network in the open dataset category.
So this case study shows you how convenient we can combine the geospatial analysis functions with KNIME, because once you change one of the parameters, you will get a result directly. So you don't need to go back and forth. If you use Python Jupyter, you will go back to jump to a line, and you will to see which line is the first line. So it's quite hard to find or change the parameters. But with KNIME, you can do that very easily. So also in my mind, I thought KNIME can work as mind mapping. So you can use that to reconstruct your idea or thoughts. So I think that's the convenience of KNIME. So I can say there is still a little bit more time. I might need to play a last video, which is it's a quite interesting video. It's about to build. So I will play the last video. So this video shows I will build a heat map based on OpenStreetMap point of interest. So many users complain that they don't have any data, but nowadays there are more and more open data sources because of the support of the citizen sites. For example, OpenStreetMap. So everyone can get information from map. So why not we can build a dashboard based on that. So here is the case study, and you can generally you can map in any kinds of the facilities or the points. For example, you can churches or parks.
First, we use the refresh button widget node to create a global update control button. Then drag in a string widget node as the city address text input port, name the variable as location, enter Cambridge, Massachusetts, USA in the default value input box, and edit the text in the label. Next, drag in OSM poise and OSM boundary map from open datasets. Link the string widget to the boundary map and set the place name as the variable location. Executing the OSM boundary map node will get the city boundary of the city of Cambridge. Then connect the OSM boundary map node to the OSM poise node. This node will obtain the points of the OpenStreetMap based on the boundary of Cambridge City. The default selection is restaurant under the amenity class. In order to set more amenity class options, we can click the OSM poise node, view the description, and click the OpenStreetMap tag info link. Select amenity in the web page and sort. Copy the first few hotspot values to Notepad and keep the tag value. Go back to KNIME, drag in the single selection widget node, and copy the value in Notepad to possible choice. Add hospital as an optional category of POI, and modify the label description. Connect it to the OSM POIs node, and adjust the flow variable setting so that we can get any POI data under any city. In the second step, we will establish a square grid to summarize and visualize the number of POIs, which is similar to the function of a spatial heat map. First drag in the Create Grid node because it allows specifying the value of the edge length. We can introduce an integer widget node to set the input window. After connecting and testing the Create Grid node, it can be found that the grid side length unit in the Create Grid node is consistent with the projection system of the input Cambridge boundary geographic data, and its unit is degree, so projection system transformation is required. Drag in two projection nodes again. The former is set to EPS 3857, and the latter is set to EPS 4326, linking the nodes to convert the unit to meters before executing Create Grid. After executing Create Grid, the unit is changed back to the original projection system. Drag in the spatial join node. Use the column filter to keep the key parameter column before execution, and use math formula to establish the value of count equals 1. Then use the math formula to construct an integer index for the grid data to facilitate subsequent attribute links. We can handle the null value of OSM data through the missing value. Connect the POI data to the upper input port of the spatial join. The grid data is located at the lower input port, and set the relationship as left join and intersect. Run node. In this way, all POI points will be attached with the attribute value of the grid data that intersects with it in space. Here, it mainly refers to the index of the grid. Use the group by node to summarize the count or category of POI points based on the grid index value. Then join the aggregated value back to the grid data and use the missing value node to handle blank values. Finally, we use the Geospatial View node for visualization. The third step is to select all nodes, package them as components, and execute them. After execution, right-click and select Interactive View component to view the dashboard that can summarize and analyze global OSM data. Here we can choose any location address, amenity tag value, or grid length size, and then update the map through refresh. Here we explore the cases of the United States, China, Germany, and Brazil.
Okay, so this is three short videos. I want to give you a taste of our geospatial analytics function, and then I will go to the general conclusion of our slides. So the first version 1.0 was released in December last year, and with KNIME Analytics platform version 4.7, and we will, as I mentioned, we will release the slightly updated version 1.1 maybe the last few days of January, or maybe the first few days of February, with KNIME Analytics platform 4.7.1. And when we want to build this, why we want to build these geospatial functions, even we can use Python scripts to finish our tasks. We found that many users complain that if you need to install or configure the Python environment, so it's quite hard for the learners or some collaborators that are not in the field of or not familiar with coding. So I sort of want to combine this function with KNIME. So if you install our extension, you don't need to configure the Python environment. Just to install that, you can use it directly. So it's quite handy. And also for in our this extension, it can support for the most common vector data such as point, line, polygon, and collections. And we are also collaborate with our colleagues. We do have some plan to develop some extension such as GeoImage, which maybe can processing remote sensing data. One of my colleagues might be leading this project. So also we are this project is a joint project developed by the colleagues at Harvard CGA. Also, I have friends at LIME. We are strongly collaborate and working on this project. So all the functions and all the coding will be in a good shape and be polished by experts. And we will also continue to work together to add more functionality and improve the usability. As I have shown you, we are keeping updating our extension. And also the feedback is always welcome. You can go to a LIME Hub community. Also, you can go to our GitHub to just put an issue for us. We will solve that directly. So this is the general background for our LIME extension. And in terms of all the functionalities, you can see there are 10 categories in the first version of LIME Geospatial Analytics extension. So the first one is spatial I/O, is including input and output. You can read and write the spatial data such as shape file, GeoJSON, and also geodatabase, which is supported by S3. I know many students at Harvard, they are using S3 ArcGIS Pro, so it can be communicated between different software. The second one is spatial calculation. You can calculate attributes such as area, nodes, and also like the coordinates, and you can use them as the information for the subsequent analysis. The third one is a spatial manipulation. You can do some buffering or multi-rim buffer, do spatial overlay and join. It's quite, and we just prepared the most popular functions for the geospatial missions. Also, the spatial transformation is mainly about how to transform from line to points, point to line. For example, we use the point to line to build the taxi trajectory with their GPS signals. So this would be quite helpful when you are dealing with some big data of spatial temporal features. For the spatial conversion, is mainly about how to convert the address to geospatial data, or convert it back, such as net none to point to net none. And also you can use the well-known text as WKB and WKT format. And the favorite one is spatial visualization. We have 4 nodes. The first two is a dynamic view, which is based on Phonium or the leaflet. And another one, as I'll show you, is Capital Geo View. That one has a very fancy interface. You also can do some 3D visualization. And for the exploratory spatial data analysis and spatial modeling, we generally use a function from the Geoda and the other spatial statistical models, such as spatial area model, spatial neg model, or spatial neg panel model, such like that. We still actually we have more functions, but we don't combine them with our first edition. We will release them in the afterwards versions. And for the location analysis, I think my second case study is about this one. The last one is open data sets. We want to combine more and more data sets for geospatial experts, because we also have already developed a nodes which can acquire data from Harvard database. So it can be very convenient. You can get data directly. You can push the data to the Harvard database. So this is generally all the several categories. And the new category is named the spatial network. It will be released in the next version. So we not only have the geospatial functionalities, we also want to provide more and more case studies to share with you. We also cooperate with a journal. It's called Urban Informatics. They also want to do we call it as interactable journal. So users can read the journal, the paper, and also they can execute the workflows with our LIME web portal-based server. And another thing I want to mention is I also cooperate with Professor 501. We have finished submitted the manuscript to the CRC press. It's called a computational method and GIS application in social science. This is a third edition, and the second edition is this thing. And we will convert the whole book into a LIME webbook. So all the functionality can be found in LIME, such that you can read the word cloud such as recognition and accessibility, spatial statistics, Monte Carlo simulation, crime simulation, you can find it. So we want to deeply combine LIME with geospatial analysis, and I want to include more people without any coding experience into our open geospatial community. So we also want to acknowledge the ASF Foundation and also the Spatial Temporal Innovation Center, and also we can include a bunch of open source Python package and a platform here. So yeah, that's it. Thank you. And we want to build a geospatial analytics for all. Yes, thanks. So I will come back.
Time for question or move on?
Yeah, I think we're ready for some questions.
Okay.
First off, we'll take some questions from the crowd here, and we'll give it a minute or two for anyone joining in online to ask some questions in the chat, and I'll get to those later. So does anyone here have any questions for our presenters? Anything about the data they ingested, the KNIME tool itself, usability, struggles, ease of use? Yes.
So how many, your workflow ran very quickly. So what is the size of the data and what did you run it on?
Okay, the size.
If you answer your question, could you please go
Yeah.
closer
Yeah.
for the online audience? And maybe
I'll repeat the question as well. So she commented on how fast the workflows ran. So she wanted to know the size of the data and if that was actually real time or sped up, or just how well KNIME processes large data sets.
Yeah, and so LIME can process like in my experience, I process like 1 gigabytes text CSV file and in that platform, and it runs very it runs fine. And for my case studies, and all the data sets they are used like for example, if you use the road network, it was like 2 megabytes, and it runs quite smooth. So I think it's and for the usually for my in my experience, I need to build the workflow. It might take like 1 day. So but it will take like 1 day to build a workflow because you have some concepts, and it also depends on what the project you are doing. But to run that, it will be very quick, and all the workflows they run like in maybe for the first like 5 case study, it might take only like 10 minutes, maybe like 5 minutes. It's even fast. Okay.
I guess the speed of processing depends on your computing resource too.
Yeah.
It's not just data size, right? If you're running it on the desktop analytics platform, right, your PC's RAM and CPU, right, computing power will impact the speed as well.
Right, so if you're running the 1 gigabyte data set and it, how long does that take and what are you running it on?
Okay, for 1 gigabytes data, I was processing is like text trajectory data. So it read the reading will take like 3 or 5 minutes in my laptop. Yeah, that's the speed. And if you want but the processing is a little bit faster than that because it will contain that in the memory of the computer. It will be faster than the reading.
So it's probably say 10 minutes on like a standard Dell, or is it a souped up Dell, or is it something else?
Yeah, it's a Dell laptop. Yes.
Do you know how much memory you have allocated?
I have 16
gigs of RAM, and then CPU processing varies between computers, but 16 is not an extraordinary amount of RAM, and RAM these days is fairly cheap. So if you needed to upgrade, I'm sure you could. But that's almost a standard laptop these days for probably what work will give you. So.
Right, so it's not a cluster or something like that. It's running
and if you do scale up and go even further, then you can integrate that into your cluster, and it will run even faster for reports and things and for more dense data sets. So.
I think most of my research are finished by my laptop. Yeah, so that's my experience.
Thank you.
Yeah.
Do we have any other questions from the audience here on site?
I think it was some wonderful use cases and a great presentation, by the way. If I think this is a new capability, right? If I'm not wrong, in KNIME, this is something new that's come in December. If we have some specific use cases which will help the community, how can we go about publishing our use cases as well? If we don't know how to code, but we want to utilize this capability, but we have a use case in mind which will further the community. So how can we do that?
Yeah, I think I would like to remind that we already released this first version on December last year,
Yes.
and we are preparing the new version. So you want to build your own use cases, and I think it's two-way. Every month on our Speed There project, we will have some training webinar, and you can get some training. So you can get familiar with the geospatial software and extensions. Then you can build it by yourself. So we already held like 4 online webinars. They will take like 3 days, but 2.5 hours per day. And the first 2 days are training. But the third day will be the case study presented by the groups. So I think after the very short time training, they can grasp how to build a webflow by themselves. I think you can do that by yourself after the very quick intro training. And also you can publish your case study on our KNIME Hub directly because it's open community, everyone can share and communicate with each other. Yeah.
Thank you.
And on top of that too, if you wanted to reach out to KNIME and ask us about any case studies or anything that's in a similar field, we're always here to kind of help people, get the right tools and work within KNIME to kind of do whatever research they need. So if we have similar case studies, we'll definitely send them your way. We have large communities of people as well, especially at Harvard and everywhere else that if they're working on something similar, very friendly and very happy to share if they can the data that they've used or workflows or maybe give you a tip. We also have the KNIME forum, which is kind of our online help forum where you can post questions, saying, hey, I want to translate this data or I'm not sure how to do this in our online community as well, are there to support you. So, and
That you said most of what I wanted to say. Just
Sure.
want to add that the Spatial Data Lab project that we're in, right? Not only building tools, but also building a repository of case studies. So what we're using is that, we'll eventually publish it all in the Dataverse platform, share with the public, and that would be packaged. The data sets or data source, if it's streaming data, the workflow, which uses all these KNIMEs and extensions and other tools, and the visualization of this sample package. But you could pick a package that kind of close to what you want to do, but not exactly what you want to do, tweak it further. Test it first, whether it behaves the way you want, and then expand it or revise it. And after you're done, please contribute back to the repository too. So that is how we plan to snowball this collaboration with KNIME as the foundation, but really at the case study level, not just at the tools and workflow level.
And absolutely, like the open source community and kind of sharing of knowledge is kind of at the heart of KNIME, and we look forward to seeing whoever puts out whatever data they have out there and helping other people kind of further along their research. And also, like Wendy said, the great part about KNIME is that it may not be your specific use case that you're looking at, but you can definitely take parts in areas where someone has already done the work, not reinvent the wheel for how to gather the data, transform some of the data, and just take that portion and explore and, change it around yourself and see if that works for you. But it is all very easily kind of ingested and, learned. The learning curve for starting is not as steep as maybe some other non-low code or, coding platforms or visualization tools as well. So,
Thank you.
absolutely.
Question. Curious, how long did it, or how much effort did it take you to make this? Is it like just you working on it for 1 year or 1 month, or what? How much effort did it take?
So you mean the
This
lab
package-
extension or the case studies?
Not the case studies, just the framework of what you've created. That's super useful.
Extension itself.
Yeah.
Extension, okay. I think extension we only develop since maybe I think it's the September last year. We decided to develop our LIME extension. So we cooperate with LIME experts, and we have two of us and another expert from LIME. So 3 of us cooperate to build this one.
Wow, that's impressive.
Thanks. Yeah. And we also want to, so in my mind, I think this project is like a small tree for open source geospatial analysis. So if with more and more users and more case studies, more models, we can make this tree got bigger, and everyone can contribute this big tree. So this is my future maybe idea goal like that.
Yeah, absolutely. And that's the community side of KNIME, is that it doesn't have to be, paid and someone is paid to build all this stuff. We have people, doing it already and putting it out there for you to use as well. So the more people using KNIME, the better KNIME gets. So awesome. Let me check the chat here to see. Okay. From Tegbaru, what procedures need to be followed to add geospatial view node into the list of KNIME nodes? This I might be able to handle. So when you develop the nodes and then you put them on KNIME Hub, someone wants to know, how do they get them into KNIME?
Yeah. I think it's so this one is the step is quite simple. So you can go to open your LIME and install extension, and you can search geospatial, and then you check our extension, then you will get this extension. Then when you open, you can access this extension under the category of community nodes. So you have all the function nodes, and it's quite easy. You don't need to configure the Python environment. I think that's only one step. You can get all of the functionalities.
Yep. We have also drag and drop from the hub as well. So there's a few ways you can do it, but also very simple. It takes, a minute or two to install it. You restart KNIME and you've got the extension installed, and you can already play around with it. So not a lot of configuration, and very easily accessible.
Yeah.
Cool. Let's see. And any plans to support reading and writing geographic data from to SQL Server or Postgres? That I'm not sure if we have quite developed yet. You can already ingest stuff from SQL or Postgres. So if the data is already there in sort of latitude, longitude, or if it's in a readable format, KNIME can pretty much take in any data source. So as long as the data is there, KNIME should be able to ingest it, and then you can pipe that into the geospatial nodes, or maybe a Python reader to clean it up a little bit more, whatever you need to do. We have the transformation in most of our nodes. So code or no code, we usually have the capability to take in any data from those two sources, Postgres and SQL, very easily ingestible. We already have connectors for both of those databases. So yeah, if you have the data, KNIME can connect to it, and I'm sure you guys can ingest it with the geospatial nodes you've already done. What database did you have it in for some of these use cases?
I think most of them are only reading the S3 format is called a geodatabase.
Okay.
Yeah. And another one is maybe I already mentioned, it's like shapefile or GeoJSON. It's not like a SQL database. But as you have mentioned, we also want to rely on the capability of LIME itself, because we don't need to build a geospatial for all kinds of data scientists, because LIME has already is a very successful data science analytics platform.
Mhm.
So we want to hug the community. So this is our original idea. Yeah. As you might know, LIME has already developed some AI-driven nodes, so you can use that, combine them with our geospatial nodes. So that can enrich our geospatial research. So this would be a double win side of geospatial researches. Yeah.
Absolutely. Great. I think that's all we have from the community. Oh, we got another one. It seems like people are very interested. What kind of exportable platforms are available for outputting results? PDF, PowerPoint, WebLink, etc. I guess I'll let you.
Oh, I thought you could be very familiar with that, because in LIME we have tons of exporting features, such as we can build a PDF or HTML that we can also build I just forget the node's name, because we can build just like a portfolio. You can export that as the format as you want. So such as a PowerPoint or such as PDF. I can remember that nodes.
Yeah. Most data formats that you can ingest, you can also export to. So yeah, PDF is accessible. Web links. You can build data apps where you can kind of export it locally to your file system, CSV, Excel, whatever. If there's an extension out there of type of file, most likely KNIME either has a node for it, or our community has usually already figured out a way to export it into that format or write it to that format. So for the most part, yes is the answer. We can export to pretty much any file type. Awesome. Great.
Okay, thanks.
Excellent. Thank you very much. I think that wraps up. I'll let you do the closing. Oh, yes. Sorry, that too.
All right, and hi everyone. Also from my side, and welcome to the second presentation. So today I'm going to show you how to build a data app using some of these geospatial nodes that Wendy and Lingbo were just presenting. So when this extension was released in December, I was super excited about it. Actually, because I didn't do any geospatial analytics before, not in my master's, not in my bachelor's. So I am fairly new to this topic. But once I started with it and tried it out the first few days, I realized that makes it super approachable to learn geospatial analytics and to use those nodes together with other nodes in the KNIME Analytics platform. And yeah, that was really amazing. And yeah, so if you're already a GeoPro, then you probably really like this extension. But if you're a beginner like me, let me tell you that it is definitely relatively fast to learn and you get results pretty fast. So the data app I'm going to show you, I actually built together with one of my colleagues, with Roberto Cadilli, so credits also go out to him. And what we are actually doing in this geospatial, data app is to blend geodata and non-geospatial data. And then, of course, typical to a data app allows some interaction for users. Now, how did we come up with the idea to build a data app using GeoNodes? And actually, there was a reason that we are using data from our Data Connect event series. I think you've all heard about Data Connect because you're here today. But if you're here for the first time and don't really know what's it actually about, so Data Connects are basically regional events that we organize on Meetup, and they serve the purpose to connect the community across the world. And usually they are hosted in the majority language of the region. And we thought we're going to use this data because we just had our 1-year anniversary and of our Data Connect event series. So we started last year in January again, and also data apps are just cool. It's nice to build a data app, it's fun to build a data app, and also it's, I think, a very nice way to provide people insights and let them interact with the data. And yeah, as a third reason, well, the new extension came out and we thought, okay, let's do something with those notes. Now, before I'm going into detail, just a quick recap what I mean when I talk about data app. So a data app is basically just a user interface where a user can interact with the data, like visualizations or exporting data or reading data. And so in the KNIME Analytics platform, you can build a data app by just simply building a workflow, or you take 2 workflows or 3 workflows, and then you wrap them in a component, and that you can then deploy as a data app. So this, what you see here, is the data app we built. This is the final workflow, how it looks in the KNIME Analytics platform. As you can see, our data app consists of 5 components, and basically in each component we have a workflow. Now, to make this accessible to the users, you are required to upload it to, for example, a KNIME Business Hub, and then you can deploy it as a data app, and then users can interact with it. And once it's deployed as a data app, each of the components, basically, you see here becomes a web page, or a page in a browser, so to say. Now, I'm not here to talk about in detail how to build data apps. We are focusing on the Geospatial extension today, and that's why I'm going to focus on 2 of the workflows that are part of our data app that do the geospatial analysis. But before doing this, I want to just quickly run through this data app with you, just that you have an idea what I'm actually talking about. What is this data app actually doing? And yeah, so as a first part, we have this about Data Connect events. This is basically just a welcoming page. There is not much interaction. Now, the second part, this actually already contains some geospatial nodes. It's a geospatial view node you can see here. And this component, or this workflow, just shows what we have done in 2022 so far, what events did we organize, in which regions, how many of them, how many people did we reach, like in a sense, how many registrations did we have, stuff like that. So it just gives a nice summary of what happened in 2022. Then there is another page. This also focuses on last year in 2022, and it gives you basically the highlights of what happened back then. Here, you don't see any geonodes. That's the reason why we didn't use anything. That's the reason why. But it's quite an interactive way how you can select the region you're interested in and select the month you're interested in, and then it just shows you all the information, like who helped in organizing, or for example, when you scroll down, then you can see that we were also able to embed YouTube, the recordings there, so you could rewatch them. So given that there is video available or recording. Then we have our 4th page, which focuses on the events in 2023. So what is planned? Just note that here we are focusing on the North America region, so on Canada and US for now. Yeah, and then in general, it's a tentative schedule, so it is subject to changes, but it just, should give you an idea what we have planned for the North America region in this coming year. And yeah, then the last page is actually of this data app is a proposal form. So if you would like to propose a data connect in your town, for example, or if you have a topic in mind and you would like to propose that, you could do it with this form. We are currently working on making this form publicly available, so please stay tuned on that. But if you have any proposal, you can also just reach out to me or any other of my colleagues that you might know. So with that being said, let's focus on our geo part. And let's start with the first workflow that I want to show you. It's the events in 2022 workflow. So the second one. So let's look at data first. What is our initial data? So we have basically just this data, which is the region in which an event happened, the number, how many events happened, and the number of registrations. Now is the question, how do we come from this data table to the final plot? We didn't have any geodata in there. We just had a name of the region. Well, what you see here is the underlying workflow. And basically to get from this data to this plot, there are basically 3 steps required. So step number 1, first of all, we had to collect all the country boundaries for all our regions. Step 2 was we had to create those buffer areas to represent the number of events in each region. And lastly, we were blending or concatenating all the results of the previous steps, and that's how we got this geospatial view. But let's talk about it a bit more in detail. So the first part, how did we collect all the country boundaries for these regions? So we started by reading in this data table that I've showed you, but then as you could see, we had some macro regions that, for example, North America, which would be the US and Canada. Also the DACH region would consist basically of Germany, Austria, and Switzerland. So what we first had to do was to expand those regions in their countries themselves. And then we were able to extract those country boundaries using this OSM boundary map node. And this OSM boundary map node just basically gives you a geometry column additional with other information, but we were interested in the geometry column that contained polygons or multi-polygons of the countries. And in the last step, because we were having those macro regions, we had to bring it back, and we had to do this, or use this union node, which was nice because if you have, for example, the country boundary for US and for Canada, you could just combine it and make a union out of it, and this would be the result. So this is basically the first layer that you have seen in our final plot. So now step 2 was creating those buffer areas. So we were looking for a way how we could basically show in the same map, in the same world map, another metric, and the metric of number of events happen in each region. So how did we do that? We were first of all extracting representative points using this geometry to point node. Then we were using the buffer node, which created a buffer area around that point, and this buffer was the size of the buffer was depending on how many events we organized. And doing so, we got this visualization here. It's basically a second layer, and you can see, for example, in the US, we organized 3 events last year, and in Brazil, for example, 1. So that's how these different size and points happened. And then last step, as I said, to just concatenate everything. It's a simple concatenation operation, so it's quite nice that you can use the existing KNIME nodes we have with those new geo nodes. And for example, we were just concatenating this geometry column so that we could overlay the different layers, and we were ending up with this. To be fair, we added some color coding here as well, which makes it look different, but here you can then see that we have our regions, and we have our circles which represent the number of events, and this color coding goes from light green to dark green, so number of registrations. So this would be the first part. Now, talking about events in 2023. The initial data we have is similar to what we had for last year. This is basically all the data we have for now. We have a location, we have a tentative month and date, and we have potential speakers and topics. Having this data, we were thinking about how could we represent this in a exciting or nice way. Of course, we could have just plot a data table and then you have a list where the events happen. Yes, we could do that, but we thought we'd do something cooler and show you which event is the next event closest to your location. So this again, the underlying workflow here. There are a bit more steps required this time. So we have 5 steps required to get from this data to a plot that basically shows you your input location and then the distance to all our events that are planned. So step 1 would have been just, we have a list of events, but we need to collect the event locations. We need to get the geodata somehow. Step 2 would be to collect the input location. So we tried to do this, or we did do it interactive, so people can just enter any location. Then step 3 would be to create those lines, because we were thinking how could we visually plot those distances. So we wanted to plot those straight lines that are connecting the input location with each of the event locations. Then step 4 would again be similar as before, concatenating all of those different geo layers, so to say. And lastly, probably the most important one, calculating the hover sign distance to find out which event is actually closest to you. Now, looking at step 1, how do we collect the locations? So this time, you can see we also use the OSM boundary map node, but this time we were only interested in the latitude and longitude, and then we converted this latitude and longitude to a point. Now this would actually be enough. We could plot those points, yes, but while we were doing this, I was figuring because we have this map quite zoomed out, because US is quite big, those points were quite small. So we added a buffer area around those points. This buffer has only, it's only there to really make the points bigger, as you can see here. I know the blue and the white is probably not the perfect contrast, but here you can see all the events, visualized as the buffer, that we have planned, or in all the locations where we have planned events for 2023. Now, step 2, how did we get the info locations? So first of all, we have this current location component here, which is there to collect the user's input location by using some widget nodes. And a widget node is there to, it basically adds the interactivity to your data app. It allows the user to select things, to filter data, or to input strings, or also to change the underlying node settings, for example, without, from the data app, but without going into the actual workflow and changing things there. So we were adding 2 widget nodes, the single selection widget node and the autocomplete text widget nodes. And they are allowing users to select a country, so either US or Canada, and enter their city and their state or province. And just again, this is just the example for North America. That's why we thought we just say US and Canada. In theory, that this would work for every location. Now, once we got this input location as a string, we again used this OSM boundary map node, and we did exactly the same thing as before. In step 1, we extracted latitude and longitude, and then we were creating a buffer area around it. And in the end, we have basically this layer, or this visualization where we only have the input location in the geospatial view. Now, step 3, how did we create those lines? This is quite an easy one. There is this points to line node, which basically just connects 2 points, and we were looping over it, so to connect always the input location with each event location, and this results in a view like this one. Only have lines. And now, to bring this all into one geospatial view, just again, a simple concatenation, and this leads us to here. I also changed the color coding here, and also the map. This I did in the configuration window of the geospatial view node directly. And step 5, as I said, probably the most important one. How did we find out which event is closest and which is the furthest away, for example? And we did this by using this hover sign distance node, which calculates the spherical distance between 2 points. We used this one and, for example, not the Euclidean distance, because the Euclidean distance wouldn't consider the curvature of the Earth. So hover sign distance is doing that. So we thought it's more accurate. And by calculating this distance, you see a data table here. It's just the outcome of the table view node. And here you see all the events, but they are sorted by distance. So in the first line, you can extract which next planned event is closest to our input location, which was Montreal in Canada. And actually, it's Boston for next month. There's actually another Data Connect next month in Boston, but with the topic of life sciences. So then the last thing we did here to get this dashboard that I showed you in the beginning. So we have now this table with the events sorted by distance. We have the plot with the lines and each input locations. And what we also did then was to add a text output widget node, and we combined it all, and this would leave us with this dashboard here, where you have on the left side, the view of the geospatial view node. On the right side, it tells you which is the next closest event, and then the bottom table just shows you all the events sorted by distance. So, and actually, with that being said, I already come to the end here. I think it's really nice with the geospatial extension, because the use case I showed you, that may not be like the typical geospatial use case for what you do geospatial analytics, but I really like it because you can just use, or it also shows how versatile geoanalytics is, and that you can just use it to basically combine it with other things and with other data analysis. For example, we used it to spice up our data app and our visualizations. And I mean, in theory, a data app like this, we could have built similarly, but then some of those functions just wouldn't be available. Like, for example, one of the location, let's say it wouldn't be available without coding. And that's what I really like, is that you have this new extension, and it easily blends with other kind of data, and you can just take these notes and throw it into your workflow and figure it out somehow. And so as I said, I'm relatively new to this field of geoanalytics, and I think you learn very quick a lot of things. And what you could also do, for example, what I think Lingbo pointed it out earlier. So with this workflow, for example, now you can just take it and adjust it to your kind of data if you have similar data. It must not be any, like we took our events data, yes, but you could take any other, events data, for example. You could plot it for concerts or for scientific conferences, so whatever you're interested in. And you could just use this in theory as a blueprint, so to say, and adjust it to your kind of data. So, one last thing, or actually two last things I want to say when we're speaking about blueprints. So these two workflows I've showed you, they are both available on the KNIME Community Hub. You can just follow those links. And the last thing I want to say is, so in case you ever wanted to be a speaker at one of our Data Connects, or if you have a very nice use case to show, please reach out to me. So you can do this either via email or LinkedIn, or you reach out to any other of our colleagues. As I said, we're also working on this proposal form, which I showed you earlier. So in case you want to propose a city or a topic for any Data Connect, please stay tuned until this data app is publicly available. And until then, also please reach out to me or any other KNIMer. And with that, thank you very much. I hope you enjoyed this not so typical use case of a geoanalysis.